Okay, so let's do a couple of examples of drawing orbital diagrams for a couple of elements. So let's start with nitrogen. Now, previously we know that nitrogen has an electron configuration of 1s2, 2s2, 2p3. But if we want to show all information about all four quantum numbers, we have to write the orbital diagram. So what would we do? Of course, we draw one box for the 1s orbital, a box for the 2s orbital, and then three boxes for the three 2p orbitals. 2p. Okay, so now we're just going to place electrons in the orbitals. We know that the 1s orbital has two electrons in it, and they have to be paired. One is spin up, one is spin down, m sub s positive 1/2, m sub s negative 1/2. Same thing goes for the 2s orbitals. Now we can see that the orbital 2p orbitals have three electrons. Now where do they go? Do two of them go in one in another? And it turns out that due to something referred to as Hund's rule, it turns out we are all going to put in singly paired electrons first, all spin up, m sub s 1/2, spin up first because that's slightly more stable. And it turns out that, of course, we can think about why we're going to put electrons in three separate orbitals first due to electronic repulsion. So if we draw a picture of the p orbitals, remember they're sort of pear-shaped lobes with a node at the center of the atom. Okay, we've got one in the z-axis, one on the y-axis, and of course one on the x-axis. So there's our three 2p orbitals. Now if we put the first electron in, let's say we put it into the p orbitals on the y-axis. That second electron, where's it going to go? Well, it still has two orbitals that it can occupy without having an electron in it. And if we throw another electron in that first orbital, there will be electron-electron repulsion, which of course will lower or increase the energy, destabilize the electron. So instead of having some repulsion, we're going to put three electrons in the three unoccupied orbitals, spin up to start off our electron configurations. Okay, so let's go to sulfur. Okay, we know that sulfur has electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p4. Again, we can use the periodic table to help us out with that. Okay, the orbital diagram would look like this. We need a box for 1s orbital, a box for the 2s, 3 for the 2p, a box for the 3s, and then the 3p again has three orbitals. If we were working with an element with a d orbitals, of course there's 5 orbitals in the d sublevel. Okay, and we're just going to fill them up. Half arrow up, then down, filling up the 2p orbital. First place them all up in the three orbitals. Then we have to go back in and refill them with an additional electron to fill them up to 6 electrons. 3s has 2 electrons. And now the 3p sublevel, or orbitals, have 4 electrons. So the first thing we do is put in 3 electrons in each of the orbitals. And then one orbital does have to have paired electrons, spin up and spin down. And so that's the orbital diagram for sulfur. Again, you can use the periodic table of the elements. Again, if you think about S blocks, if you think about S blocks, P blocks over here, D block here, and F block here. You can follow the periodic table, adding each additional electron for every space that you go through the periodic table. So for our sulfur example, we went through the 1s2, 2s2, 2p6, 3s2, and then 3p1, 2, 3, 4. For the next couple of examples, we're going to talk about zinc. We will continue. Instead of 3p4, that would be 3p6, 4s2, and then 3d10 for zinc. Here's an illustration of a couple different elements showing their electronic configuration and their orbital diagram. And again, orbital diagrams show information about all 4 quantum numbers, including the m sub s values. Spin up, plus 1/2, or spin down, minus 1/2. Okay, so here's carbon. We've shown that before, 1s2, 2s2, 2p2, and here's the orbital diagram showing the electronic configuration of carbon. Now, one property that is very useful for utilizing the orbital diagrams to explain a property is magnetism. So it turns out we're well aware of magnetic objects. We can describe objects as being either paramagnetic, and paramagnetic materials are what you would normally just think about as magnetic, meaning attracted to an external magnetic field. And why silver is paramagnetic actually is easily explained if we take a look at its orbital diagram. Now, if we go back to see the highest energy electrons in the silver, we'll notice that it is not 5s2 4d9 as we might think. It actually turns out that it takes an electronic configuration of 5s1 4d10. Okay, so let's take a look at what that looks like in terms of an orbital diagram. Okay, so silver's reduced electronic configuration and reduced orbital diagram would be silver. Previous noble gas is krypton. Okay. We're going to draw a box for the 5s, and then 4d has 5 orbitals. And as we saw, the 4d orbitals are completely filled, leaving 1 electron in the 5s. Okay, as opposed to, it's not 5s2 4d9. And the reason why is, of course, stability. It turns out that a full 4d orbitals, a full 4d sublevel, is more stable than a full 5s orbital. So what happens, instead of that electron filling up the 5s orbital, even though it's lower energy, it will hop up to the 4d orbitals and produce a 5s1 4d10 to make it more stable. Now what happens here is that leaves an unpaired electron, meaning that it's an electron in an orbital that does not have its corresponding m sub s -1 or spin down arrow, spin down, spin 1/2, -1/2 arrow. These are paired electrons. All of the electrons in the 4d sublevels are paired, and what happens is their magnetic spin cancels out. So they're not attracted to an external magnetic field. Only when you have an unpaired electron are you attracted to an external magnetic field, and we saw an example of that using silver atoms as an example to illustrate the different magnetic spin values, either attracted to the north end of the magnet or the south end of the magnet, and that's because silver has a unpaired electron. Here we can see a couple of examples of a diamagnetic material, and this is our materials or atoms that are not attracted to an external magnetic field. And actually they're slightly repelled by them. Okay, so let's look at the orbital diagram for zinc using, again, reduced electron configuration. So the previous noble gas for zinc would be argon. And then we would draw the 4s orbital and 3d. And as we saw previously on that slide, it is 4s2, 3d10. It's completely filled. So if you look at the orbital diagram, I should go all up first, then come back and give us down arrows. All electrons are paired, meaning that all of their magnetic moments are going to cancel out, so these are not going to be attracted to an external magnetic field. Now, what about zinc plus 2? Okay, removing 2 electrons from zinc, you might think that we're going to lose perhaps 1 electron from, or 2 electrons from 2 3D orbitals, leaving unpaired electrons. Well, it turns out that that can't be the case because zinc plus 2 is diamagnetic. So what actually happens, sort of like our silver example, a full 3D orbitals are more stable than a 4s orbital. So what happens is that the electrons that are removed from zinc plus 2 actually come from the 4s orbital. So that we're going to leave blank, remove those 2 electrons, and keep the 3d orbitals filled. So still, all electrons are paired, making zinc plus 2 diamagnetic. Now, it's sort of counterintuitive that if we're going to take away electrons, we'd probably take electrons from the highest energy levels that would make the ion more stable, but it turns out because the full 3D orbital makes it a little bit more stable, we actually remove them from the 4s orbitals.